Hello, so in this video we're going to talk through some stationary points examples. So here's the first curve. We've been given y equals x cubed minus 12x. We've been asked to find the stationary points and then determine their nature. So let's break it down first of all. Let's actually find the stationary points. Now just remember, a stationary point, if I get given a curve something like this, okay, the stationary points is where there's either a local maximum or a local minimum or a point of inflection. Okay, so in this case, on this curve which I've drawn over on the right hand side, and I know I haven't put any axes on, but I'm just looking at the curve and the shape of the curve. In this case, the local maximum would be this point here, and the local minimum would be this point here. Hence, they would be stationary points. They're periods on the curve where the curve is either at a maximum point or a minimum point within that local region. Okay. So just remember, at stationary points, the gradient of the curve is equal to 0. Because if I bring those back up, okay, I notice that at this point here, if I draw my tangent line in, it's a flat horizontal line, which means the gradient is 0. And similarly at that point there, the gradient of the tangent is also equal to 0. Okay, so therefore, in order to find the stationary points, because I know that the gradient of the curve at that point there, the stationary point, should be equal to 0, then I should be able to differentiate it, set it equal to 0, solve that equation, and I find my stationary points. Let me show you. Okay, so if I get given y equals x cubed minus 12x, and if I differentiate this, so dy by dx is equal to 3x squared minus 12, okay, then I know that at a stationary point, so I'm just going to write SP because I'm feeling lazy, okay, so at a stationary point, the derivative, so dy by dx, the gradient of the tangent, should be equal to 0. It's the point on the curve where the rate of change is 0. So in other words, it's not changing at that point. So therefore, if I set my 3x squared minus 12x, that's my derivative, that's my dy by dx, if I set that equal to 0 and solve it, I should be able to find the stationary points. So if I divide both sides by 3, I get x squared minus 4x equals 0. Then if I factorise an x to get x times by x minus 4 equals 0, then I'll be able to solve, well, okay, x has got to be equal to 0, or x has got to be equal to 4. Okay, now just be really careful here because the temptation at this point here is to say, x squared, x, 4x rather, I notice there's an x common to both terms, so I can just divide through by x. But of course, if you do so, you'll lose a solution, you'll lose the x equals 0. So just always make sure when you're faced with things with powers in, try and factorise rather than divide by the variable. Okay, but okay, I've found x equals 0, x equals 4. So now all I need to do is just find the corresponding y values at these points. So what does y equal when x equals 0? And what does y equal when x equals 4? Well, you notice that my original curve, my y equals x cubed minus 12x, would give me the corresponding y value. Remember, this thing says, you give me the x value, I'll find the corresponding y value. Okay, so if I stick in, first of all, well, if I take x equals 0, first of all, and if I stick that into y equals x cubed minus 12x, I find that y is equal to 0. Okay, so I find that y is equal to 0 in that case. Then if I go back and if I stick in x equals 4 up here, well, I get 4 cubed, that's 64, minus 4 times 12, that's 48. That should give me a value of 16. Okay, so that should give me a value of 16. So I know when x equals 4, y has got to be equal to 16. Therefore, the stationary points on my curve are 0, 0, and 4, 16. Okay, so those are my two stationary points which lie on my curve. Okay. Now you notice the second part of the question. I've found the stationary points, but the second part of the question says determine their nature. Okay, which is literally like saying, is it a maximum, is it a minimum, or is it a point of inflection? Now, in order to do that, I've got to think about what the curve is doing around that stationary point, okay? So let's just think about the different situations I can have, first of all. Well, if I could have a maximum, okay, so this here would be a maximum, and let's assume it's a local maximum, like the curve does other things at other places, not global maximum. But I know that a maximum, clearly, let's think about the gradients as I move from left to right. So over here, my gradient is really positive, okay, so really positive, okay. As I move from left to right, so in other words, I move along the curve, okay, the gradient at this point here, well, it's still positive, but you're happy it's less positive, okay, because now my gradient has kind of decreased in value, it's become more shallow, okay, so it's not so positive, but it is still positive. Then as I get to the stationary point, it's just established that that gradient is 0. Then as I keep going past that stationary point, I end up at this point here. Well, this point here is now negative, but it's still quite shallow negative. And then I get to this point over here, and this now is really negative, okay? So in other words, at a maximum, as I move from left to right, my gradients are changing. And how are they changing? Well, they're going from positive, so really positive, to really negative, okay? So they're kind of going from a really positive value, like 100, to maybe a not so positive value, like 10, then to 0, then to like a negative value, like negative 15, then to a really negative value, like negative 1,000, okay? So at a maximum, my gradient is changing, and it's changing so that it becomes more negative. In other words, it is decreasing in value, okay? Well, the way which I'm going to write that is I'm going to say, well, look, I know dy by dx, I know differentiating tells me how things are changing through time. So if they're decreasing, it means that my gradient, which remember is dy by dx, then my gradient is decreasing, so the rate of change of my gradient, that there is my gradient, and that there is the rate of change of my gradient. Okay, so I'm just going to put rate of change of my gradient. And of course, if I just multiply that out, that becomes d2y divided by dx squared, okay? Well, in that case, because it's decreasing, it means it's getting less. So the rate of change in my gradients is getting smaller. In other words, it is less than 0. So at a maximum, I can conclude that d2y by dx squared should be decreasing. It should be negative. And I can follow a similar kind of principle for the other situations. So for a minimum, the rate of change should be increasing, okay? So therefore d2y should be greater than 0. And at a point of inflection, it's neither increasing nor decreasing, therefore it should be equal to 0. So let me write those down. So those are the three different situations I can have. If it's a maximum or a local maximum, it means my function is decreasing, which means the rate of change of my gradients is getting less. So d2y by dx squared is less than 0. If it's a minimum, it means it's increasing, so d2y by dx squared is greater than 0. And if it's a point of inflection, in other words, it's kind of doing that sort of little rest, either from the negative or positive way, it could mean it's either neither increasing nor decreasing, which means that d2y by dx squared should be equal to 0. So let's see what's happening with our situation here, okay? So I know that dy by dx, I'm just going to write it up here for the sake of space, so you've got it all together. So I know that my gradient function for this particular curve is 3x squared minus 12, which means that the d2y by dx squared, in other words, the rate of change of my gradient, should be equal to 6x, okay? Now I just need to consider at each of my stationary points. So my first stationary point occurred when x equals 0. Okay, so I found x equals 0 first of all. Well, in that case, d2y by dx squared, all I need to do is just stick that into there. So if I stick 0 into here, I get 6 times 0, which is just equal to 0. So the fact that this comes out as 0 probably implies it's a point of inflection, okay? Obviously, the sort of correct mathematical way of saying this would be, well, we don't know, we need to do more tests, okay? But we can be pretty sure it might be a point of inflection, okay? So that's the point x equals 0, that's that stationary point there. If I look at another stationary point, okay, so if I look at the point 4 and 16, that's my other stationary point just behind me, okay, then I say, well, okay, at the point when x equals 4, what's d2y by dx squared doing, okay? So what's the rate of change of my gradient doing? All I need to do is just stick in 4 into here, and I find it's equal to 24. So therefore, because this thing is greater than 0, that implies it's probably going to be a minimum point at that point there, okay? So just determining their nature is just quite simply saying, well, differentiate again, stick in your x values or stick in your stationary point values and just find out what the second derivative is doing, okay? But hopefully that makes sense with the context of this example here and this table here. Okay, so let's work through it a little bit quicker then, with a little bit less explanation, just show you how to answer the types of questions in an exam, for example. If I give you the curve y equals 2x cubed plus 12x squared plus 20x minus 5, and again, find the stationary points, then determine their nature, okay? So first things first, I'm going to differentiate, so dy by dx, and that gives me 6x squared plus 24x plus 20, okay? And then I say, well, okay, at a stationary point, I know the derivative, so dy by dx should be equal to 0. The gradient of the tangent should be equal to 0. So in other words, I can say that 6x squared plus 24x plus 20 should be equal to 0 if it's a stationary point. Okay, so first things first, I'm going to divide everything through by 2 just to sort of see if we can simplify. So 3x squared plus 12x plus 10 equals 0. Now let's see if we can just factorise this straight off, because of course I'm going to have to solve it. Can I factorise it straight off? Possibly. However, I think I'm going to go for the quadratic formula just to make my life a little bit easier. Okay, so if I use the quadratic formula, I'm going to use x equals negative b plus or minus the square root of b squared, which is 144, minus 4 times a times c. Well, 4 times 3 is 12, times by 10, that's 120, okay? All divided by 2a, which is equal to 6, okay? If I just do a little bit of tidying up, I get x equals, well, I get negative 12, plus or minus the square root of, well, 144 take away 120, that's equal to 24, all divided by 6. All right. Fine. So let's have a look at this then. Can I do any more simplification? Possibly, if I say, well, okay, that's negative 12 plus or minus square root of 24. Does that break down? I think it does. It goes into 4. So 4 times 6, for example, that'll be 2 root 6. Okay. All divided by 6 again, and I can divide through by 2. So therefore, I get negative 6 plus or minus root 6. All divided by 3. Okay, so those are my 2 stationary points. I end up with x equals negative 6 plus root 6 over 3, or x equals negative 6 minus root 6 over 3. Now what I've got to go back and do is actually find the corresponding y coordinates, okay? So if I want to find the corresponding y coordinates, all I have to do is just stick that value into my original equation, my equation up here. So I'm just going to very quickly do that for you. So it might make sense in this case to consider by typing negative 6 plus root 6 over 3 and just typing that as my answer, okay? So finally, I find if I stick all that into a calculator and use those 2 answers and put them into my equation, I find that those are my 2 y values as well. Okay, so those are my stationary points. I should write them as stationary points. So negative 6 plus root 6 over 3. And then my y is negative 117 minus 8 root 6 over 9. And then my other stationary point is negative 6 minus root 6 over 3. And then my y value is negative 117 plus 8 root 6 over 9, like so, okay? Now to determine the nature of the stationary points, and again, I'm just going to do it up here, I need to differentiate again and then stick in my relevant x values, okay? So if I differentiate again, so d2y by dx squared, just look at this formula, differentiate it again, so I get 12x plus 24, okay? So if I stick in my first x value, which was, what was it, negative 6 plus root 6 over 3, so negative 6 plus root 6 over 3. Into here, I get d2y by dx squared. Okay, what does it come out as? Well, it comes out as 4 root 6. Okay, so 4 root 6. Well, either way, I know that is positive. So therefore, I can conclude that at that stationary point there, it's a minimum. If I do the same thing when x is equal to negative 6 minus root 6 over 3. Just remember this horrible fraction, it's just a number. Okay, so you can work with decimals if you prefer. But I just think keep it exact. So in this case, d2y by dx squared, just stick it all into my calculator, just change that positive root 6 to a negative root 6, and I find that comes out as negative 4 root 6. Either way, that comes out as negative, so therefore it must correspond to a maximum at that point there. So the process is very straightforward to deal with stationary points. First of all, differentiate, set it equal to 0 and solve that equation. Find the corresponding y values from your x values, then differentiate again to determine the nature, stick in your x values. If it's positive, it's a minimum. Negative, it's a maximum. If it's equal to 0, it's likely to be a point of inflection.